Hey everyone, Dr. Walker here. This is the second half of chapter 19. We're going to start talking about capacitors. This is video 220 and it is called Capacitor and Capacitance. Let's start off with a question. How is this possible? A defibrillator provides a large shock that can stop fibrillation. You may have seen some of these machines at various places, maybe at a mall or at a hospital. So, do you have any idea how it works? Just FYI, fibrillation, this is when your heart muscles, they twitch and they are not pumping the blood properly. So, if you have any thoughts about how this is possible, that the defibrillator helps you survive most of the time, then put it in the comments below so that we can have a discussion about it. Let's start off with the capacitor. So, what is a capacitor? It is simply two conductors with equal but opposite charge. That's all it is. They're used to store energy and also charge. By storing the charge, that's how they're storing the energy. So let's now look at capacitance. First, let's look at this picture here. This shows a capacitor. It has the two conductors that we just talked about that had opposite charges. We have a positive charge here, a negative charge on the right. You can see that we have a potential difference, delta V, between these two conductors because you have a potential VA here and a potential VB here. So this should remind you of the plates that I have been drawing in previous videos, a positive plate here and a negative plate here. So you can see there's a reason that I love drawing these because we see them again. So let's define capacitance. The ability of a system to store electric charge. It's helpful to think of it this way because then you can think of it as something having a high capacitance stores more charge. And by storing more charge, it also stores more energy. So it's a really good way to think about it. The actual definition of capacitance is a charge per voltage. So this equation here, C equals Q divided by delta V, where C is the capacitance, Q is the charge, and delta V is the potential difference. This equation agrees with what we just said. If it stores more charge, then it has a higher capacitance. You may think that the equation also means that, okay, well, if there's a higher voltage, there's less capacitance, but that's not really the case. So what's actually happening here is that the capacitor is going to store a certain amount of charge depending on the voltage applied. And I'll be showing that in an applet pretty soon towards the end of this video. Capacitance has new units. It's called a farad and it uses the letter F. Capacitance is a scalar, so we don't have to worry about any kind of directions here. So every capacitor has a certain capacitance. Let's look at a question. A 1.3 microfarad capacitor is connected to a 1.5 volt battery. What's the charge on the capacitor? So this is your turn. Try it on your own, pause the video, see how you do. The reason this was your turn is because it's a quick plug and chug type of question. We just defined the capacitance as the charge per voltage. So we can solve for Q to get C times delta V, and that will give us the amount of charge on the capacitor. It's just a product of the capacitance and the potential difference across that capacitor. So the capacitance is the 1.3 microfarads. Remember that micro is 10 to the negative 6. And then the potential difference is the 1.5 volts. That's our delta V. So if you multiply those two numbers together, then you will get letter B as your answer. We will be manipulating this equation and using this equation very often throughout the rest of this chapter. The last thing I want to do is look at this capacitance applet just to demonstrate a few things, and it would also help us for the next video dealing with a certain type of capacitor. So this is a capacitor, and the first thing that I want to show you is that there's just two plates here. We can see that when we do have a voltage, that they do have charge, you can see when this capacitor, these are two conductors here, when there's no voltage, there is no charge. Now, this capacitor has a certain capacitance. It happens to be 0.58 picofarads. Pico is 10 to the negative 12. So, increasing the voltage, as you can see, increases the charge. You can see the second graph here shows us the charge on the top plate. Increasing the voltage increases the charge on the plates. Notice that changing the voltage does not change the capacitance. So you may be wondering, well, what does change the capacitance? So what does change the capacitance is actually the geometry of the capacitor. This happens to be a parallel plate capacitor, and that's the topic of the next video. But just to demonstrate, so you can see that if you increase the area of the plates, look and see what happens to the capacitance. What do you think is going to happen? Do you think if you increase the area, the capacitance will increase or decrease? Let's take a look. If we increase it, the area, the capacitance increased. I was already at near the max, but if I start with a smaller area, you can see as I increase it, the capacitance is increasing. You can see that it's also storing more charge. As I increase it, the charge is also increasing because there's more room for more charge. And what also changes the capacitance besides the plate area is the separation between the plates. What do you think is going to happen as I decrease the separation between the plates? Do you think the capacitance will increase or decrease? Let's take a look. If I decrease the separation, the capacitance is increasing. So once again, when I decrease the separation, they're storing more charge for that given voltage. I haven't changed the voltage. For that given voltage, they're storing more charge, so they have a higher capacitance. So hopefully that made sense. One last thing I want to say while I have this very nice visual here is that the actual total charge on the capacitor is 0 because there's the same amount of charge on the top plate as there is on the bottom plate. So net charge on a capacitor is 0. So when we're talking about the charge on a capacitor, we're just talking about the charge on one of the plates, because if all capacitors had 0 charge, if we just said 0 charge, that just wouldn't be very useful. So hopefully that was a good introduction to capacitors, and we'll talk about it in a little bit more detail in the following video. See you then.